So, like Neil said, I'm Judith Evans. I'm a professor at London South Bank University. And so the plan for today is for me to provide you with an introduction to the CryoHub project. We're then going to move on to a presentation from my colleague Daniela Negro, who's going to talk a bit about the modelling that we've been doing in the project. And then a presentation from another of my colleagues, Alan Foster, who's going to be talking about thermal storage. Also, as a presenter, we've got Alan Damas. He's not here today. He's one of our partners who's from Air Liquide in France, but we've added him as he was quite influential in doing quite a bit of the work as well as Alan. And then finally, some questions. If you've got questions for us, do pop them in the question box, as Neil said, and we'll do our best to answer those towards the end of the hour. So, what is CryoHub? CryoHub is actually an acronym for a project where we're developing cryogenic energy storage at refrigerated warehouses. It's a Horizon 2020 project, and it deals with large-scale energy storage. It is a 54-month project at the moment, but we're just in the process of asking for a 6-month extension due to the COVID pandemic. We have had some delays with supplies of equipment because of the pandemic, and so most European projects are going to be allowed a 6-month extension if there were issues. So we're just in the process of applying for that. And the project started back in April 2016, and so assuming the extension gets applied, we will be finishing next year. So what are the objectives of the project? The main objective is to evaluate the potential for liquid air energy storage at refrigerated warehouses. So that's looking at energy storage at the warehouse, the use of renewable energies to actually provide that energy storage, and also providing cooling to the warehouse. We're working on the engineering solutions, also software systems. We're also disseminating information and looking at strategies for liquid air across Europe. But the main output from the project, the real big thing, is to build a demonstrator. And I'll explain a little bit more about where that's going to happen and how it's going to happen later on in the presentation. Apologies. So in terms of our partners, being a European project, we've got partners across Europe. There's 14 partners in all. I don't really have enough time to go into detail exactly who is involved and who's doing what. But as you can see, we've got a wide range of partners, and some of the partners are more technical partners, but also, as well as the technical side of the project, we do also have areas which are looking at uptake of the technology, so behavioural aspects, political aspects. And so there's sort of two parts of the project. There's a non-technical side and a technical side, because we're very aware that just providing good technology doesn't mean that technology gets taken up and used. So why are we tackling this problem? It's very clear that a greater proportion of power generation is going to be coming from renewable energy sources as we move forward. In fact, in Europe, by about 2050, about 50% of the power will be generated from renewable sources. And the main problem with renewable energy, it's not a steady and stable supply. So you're getting energy when the sun shines or when the wind blows. And so that doesn't necessarily tie in with how the grid needs to operate and how people use energy. And so moving forward, it's going to become increasingly important that you have energy storage to be able to store energy when it's generated and to be able to use it when it's needed. In terms of energy storage, there's quite a few different means of energy storage. They broadly come under 5 main headings, which are chemical, electrical, electrochemical, thermal and mechanical. CryoHub, which is liquid air energy storage, comes under the mechanical area, so similar area to compressed air, pumped hydro, flywheels. And in terms of where we stand in this map, this is a map which shows different energy storage systems. And so I don't know if you can see my mouse, but the area that we're looking at where we are, this is compressed air and pumped hydro. So we're somewhere up here on the map. So where we are is we're producing quite high amounts of power, usually more than 10 megawatts, and we're storing energy for several hours at a time. The project we're dealing with is looking probably at daily cycles, but we're looking at being able to store energy maybe for a few hours of time and to be able to use that usefully. So in terms of liquid air energy storage, there's three main parts to the system. You have a liquefaction system where you produce the liquid air, you store that, and then you use it for generation when you need it. But there is also quite a big interaction between the three different parts of the cycle. And you need to be able to use all your heating and all your coolth as best you can to get the best efficiency from the system. And Daniele will talk a bit about the efficiencies of it, but basically when you liquefy, you need to be able to use and store the heat that's generated during the liquefaction and use it in the generation, and the cooling you produce in the generation you also need to be able to use in the liquefaction, and those two processes are not concurrent, and so you have to be able to also store heating and cooling as well to make the cycle more efficient. And that's where Alan is going to explain a bit about the thermal storage systems that we've been working on, as this is a really, really important part of the cycle. And if you don't get that right, you're not going to get efficiencies that you need. So liquid air is a promising storage technology, but it's actually not a new technology by any means. And we know that systems have to be very carefully designed to achieve the commercial round trip efficiencies. That's the ratio of the energy you put in to the energy you get out. Our project is dealing with refrigerated warehouses and food factories. And we chose that because often refrigerated warehouses are in areas where renewable energies are sited. You can see the picture on the left-hand side, the third one down. That's looking down on the top of a big cold storage warehouse. And you can see that it's actually covered in solar panels. And it's not uncommon for big warehouses to have solar panels. Also, a lot of warehouses, they're located in sort of urban, semi-urban areas, or often even in the countryside. And so it's quite possible also to apply things like wind turbines. And so there's the availability to renewable energy at these sites. Warehouses are already quite familiar with grid integration. They already do something they call load shedding, which is arbitrage, where they actually reduce the temperature in frozen stores when the energy is relatively cheap, switch the cold store off when energy is expensive, and let the temperature slightly increase. And so basically they're buying energy when it's cheap and not using it when it's expensive. And so it's not necessarily a method of saving energy, but it's a method of saving money. And so I'll move on to the next slide. So there's some large benefits from energy storage to aid grid balancing. You sometimes have too much renewable energy. That's been an issue sometimes in this COVID pandemic, when sometimes energy is reduced to about a fifth of what it was before. So we need to be able to store that energy and usefully use it. Otherwise, we're basically throwing away useful energy. And also when there's high power demand, we can actually use that stored energy, because when there's high power demand on the grid, we're often bringing in inefficient generation systems. So overall, we can try and reduce the carbon used in the grid and decarbonize the grid. We can also peak shave, remove peak power requirements from the grid, which makes the grid more efficient. And we can also provide some free cooling to the cold stores during power generation. So our concept also was more than just a liquid air energy storage. We've also been looking at things like the finances behind the system. And one of the things that was clear is that although these systems are often in place for 20, 30 years, they're very, very expensive to install. And we started looking at other means that we could look to actually generate income into the system, which made it a better financial proposition today. And those things were, apart from the warehouse cooling and electricity generation, there's the possibility of the sale of liquid air or liquid nitrogen. There's also the possibility of providing fast freezing. Often warehouses are in the same location as food factories, or even the warehouses themselves sometimes freeze food. And liquid nitrogen freezers are actually very, very expensive to run. And so having a good and cheap supply of liquid nitrogen or liquid air might be a potential for food factories. Also, there's potential for transport. There's systems like the Dearman engine that uses liquid air for motive force. And there's also systems like the air liquid system, where they directly use liquid nitrogen in a transport vehicle to keep it cool. So there's a potential to be more than just a liquid air energy store. There's a potential there to be a hub as well for other items, and therefore to be able to look at what's the most efficient way to be able to use your liquid air at any particular time and then maximize your profits. In terms of the demonstrator, I spoke earlier that this is really the one massive output from the project. We're actually building a demonstration at a food warehouse. That warehouse is at one of our partners, who are called Frigologics, and they are based in Belgium. They're based on the northeastern border of Belgium, on the border with the Netherlands. You can see on the map on the top left. It's at a location called Lommel. And you can see on the bottom right, that's a diagram of the facility. And you can see already that the grey areas, they are cold storage warehouses with solar panels on. We're actually integrating into the white building, which is on the sort of middle right of the picture, which is their newest warehouse, which actually doesn't have solar panels on it, but may do in the future. And our demonstrator is going to be somewhere on the right of that and will be used for calling that particular warehouse. And the situation at the moment is that we've done the design. We're in the process of actually, we have placed purchase orders for most of the equipment, and we're in the process now of final design, integration, and actually putting the thing together. And the plan is that it should be installed around about August, September, and be operational at the end of the year. So we're really excited about that, as it's going to be a huge output from the project. So I think I've probably used most of my time. If you want any further information, we do have a website where you can look for more information. But I was going to now pass over to my colleague, Daniele Negro, who's going to talk a bit about the modelling that we've carried out in the project.
I will start sharing, but it doesn't let me because you are sharing already. So if you can stop that.
Yeah, I'll try to.
Thanks.
Stop share.
Okay. Right.
So Daniele, sorry about that. Over
no
to you.
problems. No problems. Can you see this?
I can when you maximize it. Yes, I can see it.
Right. Okay. No.
But yes, you need to go to slide 1.
Yeah, of course I was.
Yeah.
Right. So I'll be presenting some of the modeling work on the liquid energy storage system we are applying to refrigerated cold stores.
It hasn't maximized yet, Daniele, I'm afraid.
Okay.
Try again. I had this problem. It didn't work first time.
This? No? No.
Yeah, I think it's working now, yes. No.
Yeah? No?
Hang on.
It's gone slightly lined screen on my end. If you go to slideshow at the top.
Okay, just a moment. I'll share the screen.
Alternatively, I've got a copy and I can present it and you can tell me when to.
Like this?
Yes, that's it. Well done. Yeah.
Okay. So I'll be presenting some of the modeling work done for applying liquid energy storage to refrigerated cold stores within the CryoHub project. So, as Judith introduced, the problem is that the energy demand is fluctuating and ideally you want to have a constant energy demand and supply, so you don't have problems matching it. Of course, that's not reality, so you need to shave the peaks and fill the valleys of energy consumption. To do that, there are, liquid air energy storage has been suggested, but it has a very poor track record in terms of efficiencies. There are ways to improve it, of course, like anything in life, but no one has really yet demonstrated it. And it turns out that it's not a one-size-fits-all problem. You actually need to go on site and optimize it to the site conditions, and that's especially true for refrigerated warehouses. So, in terms of what was done before, initially in 1998, Mitsubishi deployed a liquid energy storage system. In fact, it was just half of a liquid energy storage system, where they would have a cryogen pump connected to a turbine and a burner to pretty much overheat the liquid air, expand it through a turbine and generate electricity. The round trip efficiency was not reported, but in this configuration, it would be pretty bad, and they didn't go any further after this project. The concept was picked up again in around 2011, 2009, 2011. There were papers published with RTs reported to be around 46%, with ways to improve it to around 90% with site-specific optimization. Following that, in 2014, HighView published a paper reporting a real-life RT of about 8%, which is nowhere near anything commercially viable. The others argued that an optimized system would achieve between 50 and 60%, but that was not proven. And that requires some ways of having some waste heat recovery of some sort. Following that, an article published by Witsi in about the same years suggested round-trip efficiency is theoretically achievable about 54 to 55%, and then Shagovelli a couple of years ago came in saying that pretty much the nominal performance of a achievable liquid energy storage system would be about 48% and a half best case. So that's where previous authors were, and the previous demonstrations were. Demonstrations actually the best achieved reported RT was 8%. So CryoHub came in following that, and the concept is, as Julie said, store renewable energy when it's generated, so at fluctuating times, and then liquefy air, store it into a cryogenic storage tank, and then evaporate it again. Store the cold you generate from the evaporation process. While you were liquefying, you were producing heat because of the compression process, so you will be feeding that back to the gasified liquid air after the evaporation, and then expand it through a series of turbines. In theory, you can also have the evaporators running freezers, ice making machines, also the refrigerated warehouse itself. There are other ways of doing it, like directly pumping liquid nitrogen into an evaporator, as the Air Liquide Blue's system does. So there are lots of ways of doing this. Ideally, you want to optimize all of the bits in this cycle, and that's where the modeling came in to give an informed decision on this. So we analyzed different sets of possible thermodynamic cycles. First of all is what will be referred as concept A, which is a standalone system where the evaporator also feeds some of the cold to the refrigerated warehouse, and that provides additional cooling to the warehouse instead of running their standard refrigeration compressors. Then in theory, on the Frigologic site, there is also the availability of using waste heat from co-located turbine, gas turbine that runs the electricity for a site nearby. It is a 5 megawatts electricity generation turbine, and that provides about 800 Celsius waste heat, which they use for pretty much boiling water, which is not efficient, but and we could use that. We could have used that to improve the efficiency of the system. Finally, there are two other possible cycles where you do something more a bit more exotic, like running a cryogenic cranking cycle and reject cold to the cold storage and take heat from the refrigerated warehouse, also providing it with electricity. And then on top of that, you can add the waste heat, which is a further complication. So in theory, all of these cycles are possible. Site-specific optimization is required. So this slide shows you the very basics of a liquefaction cycle, plus some additional interesting bits, which is something you wouldn't do on a standard liquefaction cycle. So in a standard liquefaction cycle, you will compress the air, reject the heat to ambient. So there is no energy storage, which in our system there would be. Then once you compress it and you cooled it to about as close you can to ambient, you expand the air, which is at a higher pressure, and that will cool the compressed air to a point where it liquefies, right? And then you separate the liquefied part, the gaseous part you pass through a recuperator, and that's it. It pretty much, after you inject it into this cycle, it goes around until it liquefies all the air. Obviously, there is a constant feed of inlet air, so there will be a constant feed of liquid air outside, coming out of this. The interesting bits are, as I said, the hot energy storage and the cold energy storage, in which you would have stored the cold energy you extracted during the evaporation of the liquid air you generated during this liquefaction cycle. So these are the two challenging bits in here, which are a bit novel. Hot energy storage is relatively easy, depending on the temperatures and the pressures. The cold energy storage, given it is cryogenic, it poses technical challenges which have not been solved to date or demonstrated at all. So that's where we focused our efforts, and that's what Alan and Alan are going to talk later. So in order to make sure that our models were based on reality, first of all, we passed the results to Air Liquid to simulate one of the cycles we simulated in parallel to our studies. And as you can see here, the temperatures and pressures matched within 1%. So we were relatively confident that the models we developed were in line with industry standards. So we were not doing something unachievable, or the models weren't giving results which were unreliable. So yeah, that's the validation work on the cycles simulations we done, and these are the results. So these results, these plots report the round trip efficiencies, which are the ratios between the energy output versus the energy input at different cycle parameters. So at varying the discharge pressure of the liquid air energy storage, and the cryogenic turbine inlet pressure, which is a parameter in the liquefaction cycle I showed you before. So as you increase the pressure at which you expand your gaseous air, once you evaporated it, okay, you are going to generate more energy, and that's true in general, okay? Additionally, depending on the cycles, okay, your liquid air energy storage, your liquid air storage pressure, okay, you will have different behaviors in terms of which cycle gives you the best efficiency, okay? So for example, for 36 bars liquid air storage pressure, okay, you would have a higher temperature at which the air starts liquefying, okay? So your liquefaction cycle is going to be more efficient than what you will do normally, which is 2 bars, okay? And therefore you will be extracting more liquid during your liquefaction cycle, and you'll be consuming less energy during that, which improves your round trip efficiency in general, okay? So this is what it is for standalone system, okay, where you store liquid air at 36 bars and then you regasify it and expand it at varying pressure. But as you can see, the best round trip efficiencies are about 45%, okay, which is not great and on the borderline of commercially not viable. And that doesn't change much with the cryogenic loop turbine inlet pressure. So you can make it more complicated by going for higher pressures in your cryogenic loop, but it doesn't give you that, you know, step change in performances. At 36 bars, the situation improves, as I said. Sorry, at 36 bars plus waste heat recovery at 800 Celsius, the situation improves mostly because you are extracting more energy from the gaseous air while you expand it, okay? And here you can see you are achieving round trip efficiencies without accounting for the energy cost of reheating to 800 Celsius, because we are assuming, and to be honest, a bit cheating, saying that the 800 Celsius is always available and is going to be wasted no matter what. This depends, and most authors don't say it's cheating, they say it's recycling, which is a bit convoluted to me. But anyways, you can see round trip efficiencies would increase, and you will be getting into the commercially viable side of things with round trip efficiencies above 70%, which would be great. If you reduce the liquid air storage pressure, which makes your cryogenic liquid tank less expensive because it's not as pressurized as at 36 bars, your round trip efficiencies drop about 10% from the previous case, just in the standalone cycle here. And as you can see, actually, increasing your cryogenic loop turbine inlet pressure doesn't give you an increase in round trip efficiency for going from very low pressures to very high pressures, mostly because you are spending energy in increasing the pressure of the cycle. But your cryogenic loop turbine is not efficient already, so you may just as well avoid wasting energy anyway. So that's what we found out here, which is counterintuitive when you look at the data, because here it was, you can see that you could see there is a difference in increasing the cryogenic loop turbine inlet pressure. But for very low liquid air energy storage pressure, you don't see that, you see the opposite. When you turn this on with, so you couple this with waste heat recovery, again, recovery, energy recycling, all sorts of fancy terms for saying free energy, pretty much. You are bumping up your round trip efficiencies by increasing the amount of energy you get out of this during the evaporation part of the cycle. Okay, so the evaporation, the expansion through the turbines gives you a much higher energy output, which bumps up your round trip efficiency artificially, let's say. So that's the results for this study, and yeah, this is what we are going to do in our demonstrator. We will have a liquid nitrogen tank, which we are going to evaporate again and exchange it against a heat storage material at cryogenic temperature. Then we will expand the gaseous liquid nitrogen, the gaseous nitrogen through a series of turbines. Each turbine will be dropping the temperature of the gaseous nitrogen, and therefore we will be exchanging cold with the warehouse in some ways. So this could be either the refrigeration system heat exchangers after the compression, or directly with the cold storage warehouse. It depends again on the site and what you can do with the current warehouse you have available, if you have one. In terms of round trip efficiencies, we are limited at about 15 bars liquid air, in this case liquid nitrogen supply, and depending on the discharge pressure, the best case scenario would see us achieving about 32 to 35% round trip efficiencies for very high discharge pressures. If we were free to pick a discharge pressure at our will, that would be great. We could bump it to about 100 bars and achieve about, yeah, groundbreaking round trip efficiencies here, about 3 times what Highview achieved in their previous demonstrators in 2011. But we are going to be stuck at around here, between the 10 and 20 bars mark, actually between, at around 15 bars. And therefore, the best case scenario round trip efficiency would be about 25-ish%, varying again with the cryogenic loop turbine inlet pressure. That's not great, but it is still about twice better than what was previously demonstrated. So, hey, yeah, that's the plan. In terms of further work, we are going to finish the design of and the deployment of the demonstrator this year, and model the latest achievable pressures and temperatures within the demonstrator. there will be some testing this year, hopefully starting before September. And that testing results will give us the validation of our modeling. And yeah, that's pretty much all the work that needs doing. Thanks. If you have any questions, please feel free to pop me an email. Give me a call if you want. Yeah, I'm available for a chat anytime.
Thanks, Daniele. Thank you very much.
Cheers.
I'm going to pass directly over to Alan now, who's going to talk about the thermal stores, because as we've explained before, these are actually really important to actually get good efficiencies. So Alan, over to you.
Okay, Daniele needs to unshare his screen.
Yes, of course. Done.
Yep. Okay. Let's see if I can find it.
Share screens down the bottom of
yeah,
your...
I just can't see my presentation, that's all. Hang on. I do have the presentation open, so I don't know why it's not finding it. Show all windows. Ah, show all windows, that's why. Okay.
Yeah, we can see it now. You just need to maximize it and
Yep.
you'll be away.
Okay, all good?
Lovely.
Yes.
Over to you then, Alan. Thank you very much.
Hi, yeah, so my name's Alan Foster, and I'm going to be talking about some work done on a small demonstrator thermal store, specifically a cold thermal store. And this work was done by Alain Damas at Air Liquide, who are one of the project partners. So the need for thermal storage, as Daniele explained, cryogenic energy storage inherently has low round-trip efficiencies compared to pumped hydro and lithium-ion batteries, which are in the order of 90-odd%. Okay, this is partly to do with the liquefaction being inefficient and therefore generates lots of waste heat, and also the expansion generates a lot of cold, which unless used usefully is wasted. So it's important to recycle the cold generated at expansion to help with the liquefaction and increase its efficiency. The same also goes for the heating side, but in this project we don't have a liquefaction system, so we can't recover that heat. So we were looking specifically at recovering the cold part. So we were looking at cold thermal storage, which is a bit more novel than hot thermal storage, of which there's a lot more of it. So as Judith pointed out at the beginning, the liquefaction and the expansion don't occur at the same time. So you can't exchange heat without storing it first. Now, the studies that Daniele reported show varying round-trip efficiencies, but generally what they say is that recovering the cold can increase the round-trip efficiency by about 50% to about 50%. It's a kind of a general rule of thumb, and it depends what papers you look at. So the thermal store that we, or Air Liquide had built was a packed bed thermal store. So I'll explain how that works. With a packed bed thermal store, the thermal energy is stored in basically solid filler material, which in our cases were glass beads, okay? But anything that you can pass a fluid through. So the energy is carried in and out using a fluid traveling through the packed bed. So it's a bit like, blowing air through a set of hot or cold beads effectively. Now, the big advantage of this type of thermal store is what's called a thermocline. So this diagram was kindly given permission from these people over here to use. This is actually more of a hot thermal store, but it's a good diagram to explain what's happening. So in this case, they're charging with hot fluid. Okay, and it initially would start off, say, all cold. And as the hot fluid goes in, it pushes the cold out. And effectively, you get this bit in the middle called a thermocline. which is an abrupt temperature gradient in a body marked by a layer above and below which the body is at a different temperature. That's the definition of a thermocline. So the more heat you put in, the more you push this out until the thermocline gets to the bottom, and then it's fully packed with heat. And then to discharge it, you put the cold fluid in the other way, and then effectively the thermocline pushes its way up until it's full of cold. And that you're basically moving the hot and cold out. And the advantage of this is if you can keep the thermocline small, you're not mixing the hot and the cold. You're keeping them separate. You don't want to mix them. That's the main thing of a thermal store, because you want it at a particular temperature. In our case, as cold a temperature as possible. So a small scale demonstrator was built, and this is it. So this is a thermal store. It's basically a thermal tank. In this case, these experiments were done at about atmospheric pressure, so it didn't need to be a particularly strong tank. But in real systems, the thermal store is likely to be high pressure, so you're going to need something stronger than this. You have a tank of liquid nitrogen, and then you feed the liquid nitrogen into an evaporator. In this case, the evaporator is actually inside this refrigerated vehicle designed for expanding liquid nitrogen. And then you get cold gas, which comes into the thermal store. And then we measure temperatures, pressures, mass flow rates on a data acquisition system. So inside the thermal tank, so this is a description of the thermal tank. We've got 6 thermocouples down the axial center going from the top and the bottom, and another 6 at the edges in the walls. So we can see the thermocline moving backwards and forwards. We can also see the edge effects and things like that. The thermocouples were type 2 thermocouples to measure the temperature, and we also measured pressure drop and flow rate of nitrogen. The bed in our case was 0.8 meters in diameter and 0.6 meters high, and it was filled with these soda lime glass spheres of 3¼ millimeter diameter. So we ended up with 147 kilograms of these glass beads in here at 39% porosity. Obviously, in a real system, this is all going to be much bigger scale. This is very much a small scale system that was being tested. One of the interesting things when you're storing cold at cryogenic temperatures is how the specific heat capacity of the material drops with temperature. We're very used to specific heat capacity being reasonably constant. But as you start going down to cryogenic temperatures, so this is in temperature in Kelvin. So we're looking at, say, minus 150 degrees Celsius, which is about 100 degree Kelvin, compared to ambient at about 300 degree Kelvin. You can see the specific heat capacity comes down by 1/3. So the ability for the solid material to hold the coolth is reduced by a factor of 3 once you get down to the cold temperatures. With our particular thermal store, these are the stages in operation and how it works. So this is our thermal store. We first of all charge it through the bottom. So we put cold air in, and this TF bottom will basically measure the temperature of the cold gas going in. And then this will give us a thermocline as the cold moves its way up through the gravel pack, and then at some point reaches the top. And when we see the cold reach the top, then the system is charged. And obviously, as the cold is going through, it's pushing ambient air, or the temperature of the air, or the nitrogen, I should say, that was in the vessel being pushed out. Then we store, because the whole point of this is to store. And in storage, we want to maintain the cold as long as possible. So it's a vacuum insulated vessel to try and keep it as cold as long as possible. And then at some point when it's needed again, you discharge, and you basically blow ambient nitrogen through the top in the opposite direction, push the cold air out, and then you're getting what you want, which is cold nitrogen coming out the bottom. These are the kind of temperature slopes that you get from the thermocouple. So we're looking, what we've done here is, because the tests were done at many different conditions, so different temperatures in, different temperatures out, we've dimensionalized it so we can plot them all on the same graph. So 1 effectively is the ambient temperature. So this is the temperature we're measuring at the outlet. Initially, it's at ambient temperature. When it gets down to 0, it's measuring the cold temperature that's gone in, say minus 150 degrees Celsius. So what you see is as you start blowing in, the nitrogen is 1800 seconds, about half an hour before you see any cold coming out. And obviously that's because the cold is filling up the solid filling material and not coming out, which is what you want. Then you get an abrupt temperature change where the temperature drops rapidly. This is your thermocline. And then at some point you get down to a value here where it's basically filled with cold. So there's no point of going on any further. And as you can see, this is the flow rates of nitrogen. The faster you flow the nitrogen through, the quicker it comes out the other end, quite obvious. But also the faster you flow it through, the sharper the thermocline, which is a benefit because we want a sharp thermocline for efficiency's sake. Then we have the storage. So we did a number of different experiments, once again, all at different conditions. But the general thing is, this is the storage efficiency. So that's basically completely full of cold. And this is how much of it's leaked out in that time. So in 2 hours, you're leaking out about 5.5% of what you've stored. And in 24 hours, you're leaking out about 37% or so. So this is obviously quite important because we want as much back as we put in. So the longer you leave it, the more it leaks out, obviously. Then when it comes to discharge, so 0 here. So initially, it's when you turn it on, you're getting cold coming out, and you want the cold coming out for as long as you can. And then at some point, it starts warming up, and that really means is that you're now seeing the thermocline pushing out of the top of the thermal store. Okay, and once again, the faster the flow rates, the quicker it comes out. So it's about 2,000 to 4,000 seconds before it comes out the other end. So for the different experiments that we did, different flow rates, different delta T's, so that's just the temperature difference between in and out. If we just look at specifically the mean ones for now, dimension T outlet is 0.9, so this is the point that you stop. So with this one, when we say dimension T outlet is 0.9, we're basically saying we're stopping when the thermocline has just reached the top. So the thermocline is staying in the thermal store. This one, we're keeping going until you've actually got proper cold coming out of the top. So you've actually pushed the thermal store out, the thermocline out the thermal store. And the difference between the two is if you keep the thermal store in, then you don't have as much cold capacity because you haven't filled it up as much with cold. So you've got 2.4 kilowatt hours as opposed to 2.9 kilowatt hours. But because you haven't pushed out the thermocline, you haven't wasted that cold. So your efficiency is higher, 90% to 82%. So depending on what you do, you get different, whether you keep the thermocline in or not, you get different capacity and different efficiency, which is an important point. Efficiency of discharging is lower than it was for charging. In terms of energy recovered, we got about 2.1 kilowatts, and efficiency is lower, down to about 74%. Here, we only look at stopping when the thermocline is still in the thermal store. There's not much point pushing out the thermocline because you don't, it's once the temperature goes up, it's no longer any use to you if you're going to recycle this back to a liquefaction system. So the conclusions from this work is that the round-trip efficiency of the thermal store, I'm talking about here, not of the whole cryogenic energy system, depends on whether the thermocline remains in the bed during charging. If the thermocline exits the bed, it gives a lower efficiency, 7.6% lower, but a higher capacity, 20% higher. The discharge efficiency was 74%, which was lower than the charge efficiency, which is 82%. And this is to do with the thermocline being thicker. If we look at basically analysis of all the values we've got to try and work out what the round trip efficiency of the thermal storage is, what I mean by that is the amount of energy you've put in or coolth you put into what you get back out again. If you looked at 1 hour of storage, you're looking at between 60 and 65%. So you're getting back 60 to 65% of the cooling you put in. For 24-hour storage, this drops to 45 to 49%. So that's basically what we've learned from doing the thermal storage work. And these kind of information is then useful in helping us with the design of the thermal store in the actual liquid air energy system itself, and is also applicable to other cryogenic energy systems. Okay, so that's it. Thank you very much.
Very good.
Thank you, Alan.
I will try and unshare my screen. Oh, I don't know how to. Stop
Top,
share.
Yeah.
Stop share. Okay.
Okay. Thank you very much. Thanks, Daniele. Thanks, Alan. We've got one question that's come in. Oh, another one's just come in as well. So the first question that came in was about massive spring energy storage, which was, how do you rate using massive spring energy storage when energy is produced via renewable energy and then letting the springs unwind and release energy when needed? So a sort of different technology. I don't know if either of you have got any comments.
Yeah, you can do that instead of with springs, with trains up the hills. They are doing that in England already. I mean, there is a company trying to. It is pretty much similar to a gravimetric system where you use pump hydro instead. It is extremely similar. Just if you do it with springs, it's more complicated.
Okay. Thank you very much. At the moment, there's no other questions.
Well, there is another question about the length of storage. You can see it there.
Okay. So it's available,
anyone?
both and likely to be required.
Yes. This maybe I could come in on here. The liquid air energy storage is really better for long-term storage rather than the short-term storage. And you are right that there's different reasons why you would want both. So short-term storage is, at the moment, is being perhaps very well met by batteries that provide you very quick frequency control. And batteries is perhaps the best way of doing that because you need something very rapid. The problem with things like batteries is they don't scale very well when you come to long storage, because if you want to move from storage of seconds, minutes to hours, the battery becomes massive. But with the liquid air energy storage, because the storage is it's basically in the liquid air or the liquid nitrogen, the system doesn't get any bigger, just the tank that you store it in gets bigger. And the cost of the tank storing liquid nitrogen is very small compared to the liquefaction system, the turbines, etc. So liquid air energy storage is really suitable for the longer term storage, which is the thing really that isn't being well met at the moment by other techniques.
There is a flip side to that, though. It is very much more useful to the grid to have very, very short response energy storage systems which can react in milliseconds. Mostly because the problem is, I mean, you can turn on and off gas-fired energy production plants like gas turbines in about 10, 20 minutes, and you can provide as much energy as you want. And after that, pretty much time to respond, it doesn't become more useful, okay? So you need something that's quick, that you can turn on in like a minute, okay, before the other energy production plants come in. In terms of very long duration, there is almost no value in storing energy for months. That is pretty pointless unless you have, a pumped hydro. You cannot do that anyway, and most of your efficiency is lost. So there is no point.
I think the overall point is that there are lots of different methods of storing energy, and they have different advantages and disadvantages. And so you're not probably going to end up with one that's going to be the only one that's used in the future. There's probably going to be a mix of different systems that are used, and some of them are going to have very fast response, some of them are going to have longer term response. So I think
worth bearing in mind, though, that you won't be able theoretically to turn on gas-powered things in the future. So they are going to have to find
yes, I
other,
also want my
other ways of
unicorn,
bringing
Alan.
on power.
I think probably it's a very good point, but Neil, I think we're probably coming towards the end, and we probably need to be tying up at this point, as we're almost out of time.
Thank you so much. Yeah, it's been brilliant. Thank you. Any other questions that come in, I'll be sure to send them your way.
Yeah, please just send us any other
Cheers.
questions. Sorry, we've got to cut it short, but I think we've got 2 minutes left and we need to hand over to the next presenters. So please send us any questions if there's anything you were wanting to ask us. Thank you.
Thank you very much, Judith, Daniele, Alan. Thank you so much.
Bye. Thank you for sorting everything out.
Thank you.
Thank you.
Bye-bye.
Thank you.